and I don't know how to click that. There we go. Sorry. Okay, yeah, now you're free to tweet, talk about anything. We're out of the embargoed part of the talk, and gonna move on to what JWST can do for terrestrial planets. So JWST is going to be really amazing for looking at terrestrial exoplanets. And part of the reason for that is just going to be the new wavelength regime JWST is giving us access to. So here I'm just plotting the fluxes that you get for a black body at a set of different temperatures, 2000, 1700, and 300 Kelvin. And with the Hubble Space Telescope, it covered this wavelength range spanning from the near UV to the near infrared, at least for what we were able to use to study exoplanets. And in this wavelength regime, it was really optimized for studying things that were in that around 1000 to 2000 Kelvin range, because those are the objects that were putting out most of their light at their wavelengths. So HST taught us a lot about hot Jupiters, but it really couldn't do much for habitable zone planets or anything like that, because there's just not a lot of flux coming out at those wavelengths. On the other hand, JWST is covering this much wider wavelength range, and particularly its mid-infrared instrument MIRI is extending to these much longer wavelengths. So it can cover the peak fluxes for black bodies all the way out to much colder temperatures. So even just for that reason, JWST is going to be really great for studying terrestrial planets, and in particular habitable zone planets. And so particularly when we talk about looking at terrestrial planets with JWST, JWST is going to be looking at habitable zone planets around M dwarfs. So this might be review for a lot of you, considering this is an astrobiology colloquium, but I thought I'd just quickly go through it in case anyone isn't on the M dwarf train yet. So there's several reasons why JWST is going to be much better at looking at planets around M dwarfs than sun-like stars. One is just that the habitable zones of M dwarfs are much closer in, which means that a habitable zone planet will transit many more times a year. So if we were trying to look at a habitable zone planet around the sun, the habitable zone is at about 1 AU. So the planet would have an orbital period of about a year. So if you're trying to observe it transiting multiple times, you'd have to wait a year every single time to observe a single transit. On the other hand, for an M dwarf, a typical M dwarf might have a habitable zone at about 0.06 AU, where the planet would have an orbital period of just around like 10 to 20 days. So in that case, you can observe several transits much more frequently to build up the signal to noise you need to actually look at the atmospheres of these planets. Another reason is simply the probability of transiting is much higher for an M dwarf habitable zone planet, again, because it's so much closer in. And that's just because if you imagine for a transit, we have to be seeing the planet go in front of the star from our perspective. So there's a very small range of inclinations that are allowed for the planet to actually transit. And for a sun-like star where the habitable zone is much further out, that range of inclinations gets even smaller. So a planet in the habitable zone of an M dwarf has about a 4 times higher probability of transiting than a sun-like star planet. And then finally, all right, good. Finally, the transit depth is just bigger as well, because the transit depth depends on the relative size of the planet and the star. So since M dwarfs are so much smaller, it's going to be much easier to see terrestrial planets around these smaller stars. But we have a lot of questions about what planets around M dwarfs might be like. And in particular, one I'm going to focus on today is whether M dwarf terrestrial planets could hold on to atmospheres for long enough for life to develop at all. So M dwarfs are much more active than sun-like stars, particularly at younger ages. And it's possible that the high energy flares from M dwarfs could completely strip atmospheres off altogether before life has a chance to develop on these planets. So kind of the first order question I'm interested in answering with JWST is whether terrestrial planets around M dwarfs can hold on to atmospheres at all for geologic timescales. So there are several different ways we can try and figure out whether terrestrial planets have atmospheres. So the first is if we observe them in transit, we can see the starlight getting filtered through the planet's atmosphere, and we can look for the absorption features that would indicate to us that that planet does indeed have an atmosphere. So this is just one example from a paper by Jake Lustig-Jaeger looking at the absorption features we might be able to see on TRAPPIST-1e if we looked at it with JWST. And this is, of course, what we want to do if we want to look for, biosignatures or something like that. This is going to be the way to do it. But if we're just trying to say, first order, does this planet have an atmosphere? It can take a while to actually answer that question with transit observations. And the reason is that in transit, clouds can actually block out that signal that you could see. And if you observe a flat line in transit, you have no way of knowing, am I looking at a planet without an atmosphere? Am I looking at a planet that has an atmosphere, but it's got clouds in it? Or am I looking at a planet that has an atmosphere, but it's so high mean molecular weight that I haven't observed it enough times to see any of those absorption features pop out? That also means that we would have to observe a lot of stacked transits to see these clear absorption features. So it could take a significant amount of telescope time. Of course, that's worth investing if your planet has an atmosphere and you're looking for things like biosignatures. But we want to know first whether this is kind of a likely outcome for M-dwarf planets, whether they're likely to have atmospheres before we put in all of that telescope time. So another way you could look for an atmosphere on a terrestrial planet is you could observe a phase curve, where you're observing the thermal emission from the planet as it goes through one orbit around the star. So for the planets that are in habitable zones, they're interior to the habitable zone around M-dwarfs. They're fairly close into the star. So generally, we assume that they would be synchronously rotating. So they'll have one constant day side facing the star and one constant night side facing away. And if that's the case, then what you're essentially observing during a phase curve is the temperature of the planet as a function of longitude as it rotates around the star. So this has been done already, actually, for some terrestrial planets. This is an example for the terrestrial planet LHS 3844b, which was observed with the Spitzer Space Telescope by Kreidberg et al. In 2019. And you can see they observed this flux of the planet throughout its orbit. And what they found was that it had this really drastic temperature contrast between the day side and the night side, indicating that it probably didn't have at least a thick atmosphere. So that is definitely one way to look for atmospheres. But again, the problem with that is that phase curves take a long time to observe. They can take of order 1 to a few days to watch a planet go all the way around the star. So again, when we're talking about using a precious resource like JWST, we want to know, is there a way we can do this better and quicker? So what I'm going to be talking about today is actually observing these planets in secondary eclipse, where we also see thermal emission from the planet, but we're just looking at its day side. And I'm going to talk a little bit about a method that I developed along with Daniel Cole and Mathieu Malik to use MIRI's low resolution spectrometer to do secondary eclipse broadband photometry and use that to tell whether these planets have atmospheres. So the basic idea of this secondary eclipse photometry method relies on what I said earlier. If we have a synchronously rotating planet and it doesn't have an atmosphere, it will have a hot day side and a cold night side. Then if you add an atmosphere on top of that, the atmosphere will decrease the eclipse depth or cool down the day side of the planet in one of two ways. The first is that an atmosphere that's thicker than about a bar can transport heat around to the night side with atmospheric circulation. So here I'm showing some models that Daniel Cole made that are showing the temperature or the flux ratio as a function of the phase in the orbit. So here the secondary eclipse is at 0.5. And these are for 3 different hot rocky planets. And the dotted line here, the dotted black line, shows the phase variation you get for a planet that's just a bare rock. And then these colored lines show progressively adding a thicker and thicker atmosphere on top of that. So once you get to an atmosphere that's about a bar thickness or thicker, you can see that this temperature that you would observe in secondary eclipse decreases significantly. Compared to what you'd be able to get as a signal size with observing the planet with MIRI LRS. And that's what these black points over to the side show. Those are estimates of error bars for each of these planets observed with MIRI. All right, so that's the first way that an atmosphere can decrease the secondary eclipse depth. Then the second way is that an atmosphere can also host high albedo clouds or hazes. So here I'm showing a plot I made that just shows me scattering calculations and the resulting albedo you get for cloud particles at a variety of different particle radii and cloud column masses. And then to kind of guide your intuition, the stars on here show typical cloud properties for the Earth, for Mars, and then for the hazes that form in the upper level of Venus's atmosphere. So if your atmosphere isn't thick enough to distribute a lot of that heat around, it could still end up decreasing the temperature you see in secondary eclipse just by hosting high albedo clouds. All right, so the idea that we've got then to kind of summarize this idea is that we expect that a planet that is just a bare rock will be very hot on the day side. And so there's essentially a minimum temperature or a minimum secondary eclipse depth that would be consistent with a bare rock planet. Then if we were to observe a secondary eclipse that was shallower than that, which means we observe a planet that's colder than that, then we could infer that the planet must have an atmosphere. Now, there's one kind of subtlety to this that you may have thought of already, which is how could we tell the difference between a high albedo atmosphere and a high albedo surface? So on Earth, we have plenty of surface types that are high albedo enough, you could probably confuse them with clouds. We've got snow, rocks like the White Cliffs of Dover, which is a limestone, or granites like the one here from Yosemite. So all of these are really high albedo and could potentially be confused with an atmosphere. So what we did in my paper is we actually looked at reflectance spectra of all of the common surfaces that we've seen to exist on terrestrial planets in the solar system. And we used those to kind of see for what types of planets could we say that we wouldn't expect these higher albedo surfaces to exist, and so we wouldn't have to worry about confusing a high albedo surface with an atmosphere. And what we found is we can kind of divide the surfaces that we see on solar system terrestrial planets into two categories. So the first are the ones shown with red lines here. So these are all relatively low albedo surfaces. So those ones would not be easily confused with an atmosphere. And then the second category are the blue lines on here, which are relatively high albedo surfaces. And it turns out that everything that's a relatively high albedo surface we see on a terrestrial planet is water rich somehow. So either an ice rich surface or minerals like granite and clay, which incorporate water into the mineral structure. So in some way you need water to form all of these surfaces. So what that means is that if we look at a planet that's at a habitable temperature below the runaway greenhouse, we could have some of these water-rich surfaces existing, which would mean that the surface could have a high albedo, and so we wouldn't be able to definitively say if we see a cold dayside, it must be an atmosphere. However, if we move to slightly warmer planets, if we go beyond the runaway greenhouse limit, which in our paper we conservatively set at a substellar temperature of 410 Kelvin, then any of those water-rich surfaces would not be expected to form anymore. So at those higher temperatures, we would expect only the low albedo surfaces to exist. And so then if we saw a cold temperature in secondary eclipse, we could say, ah, yes, that must be an atmosphere. We can't confuse that with a high albedo surface. And then it turns out that as you get to even higher temperatures, this assumption actually starts to break down again, because when you get to a substellar temperature of about 1250 Kelvin, the rock starts to partially devolatilize. So essentially at that temperature, what you're getting is a tenuous rock vapor atmosphere over a melting rock surface. And when the rock partially volatilizes, the more volatile parts of the rock evaporate out first, and what you're left behind with on the surface of the planet is corundum, or rubies and sapphires. And it turns out that that's pretty high albedo as well. So if we looked at one of these hot planets, we might be interested in those for some future interstellar mining operations, but we wouldn't be able to definitively say if we looked at this planet that if we see a cold temperature, it must mean an atmosphere. So we're actually going to be using this secondary eclipse photometry method this year. So unfortunately, we're not getting data until May or June. But I'm leading a program to look at the terrestrial planet GL486b using this secondary eclipse method. So this planet's about 700 Kelvin, and we're going to be observing two secondary eclipses, which here I'm showing are simulated data from that program. This is what we think we'll be able to see. And two eclipses should allow us to differentiate between a hotter bare rock surface and a cooler planet with an atmosphere at about a 5 sigma significance. But of course, this whole idea is we're getting a spectrum from MIRI low resolution spectrometry, and we're summing that all up to get this one temperature measurement. But we do still get that spectral information. So if we do detect an atmosphere on this planet, we'll be able to separate those data back out into a spectrum and look for molecular features in the atmosphere. So here I'm showing, again, what we think our simulated data would look like compared to a few possible atmospheric compositions we could observe on this planet if it had an Earth-like, a Venus-like atmosphere, or a 100% water steam atmosphere. And we should be able to differentiate between these cases at about 3 sigma. And then really excitingly too, since we're observing in secondary eclipse, if there isn't an atmosphere, that isn't just the end of the game, we got a flat line, we go home. If there isn't an atmosphere, then we still get this secondary eclipse spectrum, but what we're seeing then is thermal emission from the surface of the planet itself. So we can again look at this spectrum, but we can look for bumps due to mineralogical features on the surface of the planet. So if it doesn't have an atmosphere, we'll be able to do, for the first time, what I like to call exogeology, and actually get a measurement of the surface composition of a terrestrial planet outside the solar system. So this could give us our first chance to start looking at whether planets outside the solar system have the same surface types as what we see in our own terrestrial planets. So that's just, we're doing this one program with one planet, but what we're hoping to do in the future is expand this into a larger program to look at a lot of different planets in secondary eclipse, because this method should really quickly, within 1 or 2 observations, be able to tell whether these planets do or don't have atmospheres. So the idea is that this method could give us a really quick way to kind of get a statistical measure of how likely atmospheres are on M-dwarf terrestrial planets, which could really teach us something about how prevalent atmospheric loss is around M-dwarfs and what influence the early activity of M-dwarfs might have on habitability. So in this plot, I'm just showing all of the different terrestrial planets that have been detected so far. And I'm plotting their equilibrium temperature versus their eclipse spectroscopy metric, which was developed by Eliza Kempton as a way to say how easy it is to observe these planets in secondary eclipse. And this gray shaded area is the ones that are too cold and too difficult to observe to be able to make this kind of inference with just a single secondary eclipse observation. But all the ones above that are planets that we could potentially observe with just one secondary eclipse with this method. So one more thing I want to point out while I'm on this slide is that I've highlighted the habitable zone as well in blue here. And something you may have noticed from earlier is that I said that it only works well for planets that are interior to that runaway greenhouse limit, so that they're hot enough that they can't have water-rich surfaces. So by definition, the inner edge of the habitable zone is the runaway greenhouse limit. And so that means that this method will not work for detecting atmospheres on habitable zone planets. But it still can teach us a lot, I think, about what we might expect to see on habitable planets around M-dwarfs, because it should really teach us a lot about the atmospheric evolution in a statistical sense of this population of M-dwarf terrestrial planets. All right, so I guess I talked fast because we have a lot of time left, so I hope you all have good questions. But before I end, I really quickly want to acknowledge all of my co-authors and collaborators on this project, particularly Daniel Cole and Mathieu Malik, who kind of co-led this project with me. Also, the entire JWST Transiting Exoplanet Early Release Science for being so kind as to let me give you a sneak peek of some of our results before they're really public yet. I also want to acknowledge funding from the NASA Sagan Fellowship, and I want to respectfully acknowledge that the land we're gathered on today touches the shared waters of the tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. So just to conclude, secondary eclipse photometry is an efficient method for detecting atmospheres on terrestrial planets. And atmospheres can be detected through this method because they decrease the secondary eclipse depth either through transporting heat around to the colder night side or through hosting high albedo clouds. For planets that have substellar temperatures between about 410 Kelvin and 1250 Kelvin, this means that if we observe a cooler temperature in secondary eclipse, we can unambiguously identify that as an atmosphere on that planet. And we're going to have real results using this method from JWST in just a few months, so stay tuned for that. So thanks again so much for inviting me, and I'd be happy to take any questions.
Well, thank you so much, Megan. We'll look forward to seeing those results. So yeah, plenty of time for questions, both from the room and online. Yeah.
Hi, really good talk. It was very exciting. I had a question towards some of the bias that you may expect from that kind of observation, in the sense that, if I understood well, the larger the planet, like the larger the rocky planet, the easier it will be to detect the secondary eclipses and the atmospheric composition, even the surface composition. And so, if the rocky planet is larger, we should expect it to be able to keep its magnetic field longer, and so it will be able to protect the atmosphere longer. Right? And so I'm just wondering what are your thoughts on this? Like, should we expect to have a bias towards finding more planets with atmospheres because they're bigger and the magnetosphere is able to be kept that way?
Yeah, that's an interesting question. Yeah, I don't know actually. I mean, it's interesting because I guess the like early activity M-Dwarfs period. I guess the main question I would have for you then is like, how long does it take to like spin up a dynamo in a rocky planet, basically? Because I'm wondering whether it would like basically all of this early M-Dwarf activity would happen before the planet had even developed a dynamo. But I don't know the answer to that. So no, I think that's possible. Yeah, that would be very interesting to see.
Yeah.
I'm interested in the gas giant results you showed with JWST, and as much as how the predictions that were made before the observations compare with the actual transmission spectra. Do they match well, or if you need a cherry pick them match well?
Yeah,
Sorry, could you, I forgot to say, could you repeat for the
questions?
online
Yeah, sorry. So the question was, how well do the JWST observations of the hot Jupiters that I showed at the beginning match the expectations that we had for what they would look like? And the answer is, so at least in the case of WASP 39, it actually matches quite well what we saw with Hubble. Which is kind of why it's so interesting that we're getting very different results, because with Hubble, with this single feature, the best fit models were showing like no clouds and a solar metallicity. And now that we have multiple features with JWST, that feature is actually quite well matched by what we see with JWST, but with more additional features, the models are now preferring a higher metallicity and clouds. And so it's interesting to see how like even our expectations from HST have like already kind of been thrown to the wind. Yeah. Yeah, oh, can I don't know how to see that from here. Oh, now it popped up here, okay. Yeah, so how likely or unlikely is it that a habitable zone planet would lose its atmosphere if an inner non-habitable zone planet had retained its atmosphere? Yeah, that's a good question. So kind of the underlying assumption behind this work looking at like interior to habitable zone planets is that the closer you are to the star, the easier it is to lose your atmosphere, because the more you're getting blasted by that radiation. So I mean, I don't know if you could construe a case where like the exterior planet would lose its atmosphere and the interior one wouldn't. Maybe if they're like very different in mass, and so like one had a harder time holding onto it in the first place. But yeah, kind of the working assumption is like, if something interior to the habitable zone can hold its atmosphere, then an identical planet that's in the habitable zone should also be able to hold on to its atmosphere, because it's basically just the same planet, but getting hit with less radiation. Yeah.
Question, yeah?
I was wondering if you could describe more about how you get the aluminum oxide surface, because you have to get rid of 90 or 99% of it.
Yeah.
And also, thinking along the lines, there you might get a high albedo thing, but it's also imaginable that you could go the other direction and have a carbon surface, because in carbonaceous chondrites, there's 5 times as much carbon as there is aluminum.
Yeah.
And carbon is actually extremely refractory as long as it's reducing conditions. It's actually the most refractory solid. The conditions are right.
Oh,
So,
interesting.
what are the possibilities of getting actually getting an aluminum oxide surface and even getting a carbon surface?
Yeah. So I don't know about the possibility of getting a, repeat the question. Right. Gosh, sorry. I'm so bad at this. The question was, like the aluminum oxide is essentially the very last component that would be left. And so, like, what are the odds of actually seeing a planet with that? And then also, would it be possible to see a planet that had a refractory carbon surface, since carbonaceous chondrites are expected to be common? If I interpreted that right. Okay, perfect. All right. So to answer, I guess, the first part of your question, we were basically assuming here that we're going to be like very unlucky. We're not catching a planet at any sort of special point where it's evolving or something. So essentially what we were doing is we were saying, if you took a planet and put it somewhere and left it there for like 2 billion years, at what point would we expect that over billions of years timescales, everything would evaporate and leave behind a like corundum surface? So that's kind of like the timescales we were looking at for like how long would it take it to evaporate away the rest of the rock. So at those like temperatures near that cutoff point, yeah, it takes like several billion years for it to kind of equilibrate, I guess, into a state where that's basically all that's left on the surface. For your question about carbon surface, I don't actually know about that. I don't think we looked into that very much, but I'd be very interested to hear more about that, because I guess if that were the more likely outcome, that would suggest then that this could work even for hotter planets. You might still expect them to be dark. So yeah.
Really fascinating talk. As a planetary geologist, I wanted to ask more about exogeology. So you mentioned that if there's no atmosphere, we can see down to the surface. I think that's really interesting. What kind of things could we learn about the exoplanet from that? Could you distinguish granite from ice?
Yeah. So the question was, I remembered this time. The question was, what kinds of things would we be able to learn about a planet by actually seeing the surface composition if it doesn't have an atmosphere? So kind of the like broad scale thing that we'd be able to see is essentially, we're not, dividing the surface into different regions or something. We're just getting one spectrum. So if the surface were dominated by like a single composition, we might be able to see that. So if like generally the whole planet was basalt, we might be able to see like a spectrum that's consistent with basalt, or if the whole planet was something else. Something that's, I think, an interesting thing that would be cool to look into more is like, what if these planets had like an ocean rock composition and a continental crust composition, like, so then you might get some sort of, if you're seeing a planet that's half continental crust and half oceanic crust, you might end up with a eclipse spectrum that looks like some mix of those two. So then you'd probably have to do some interpretation of like what exactly you were looking at. But yeah, I think like the level of detail we'd probably be able to get out would be just like, if there's one majority component covering the planet, what is the mineral makeup of that?
And a follow-up question to that, like, and what would be the maximum atmospheric pressure where you could do that?
Yeah, that's a good question. So that was, what's the maximum atmospheric pressure where you can actually sense the surface? So I guess that depends on how cloudy the atmosphere is. So if the atmosphere doesn't have any clouds, I don't have like a solid number, but like it shouldn't be too difficult. Like for example, when it's not a cloudy day on Mars, you can see down to the surface very easily. So something like that thickness you'd be able to do. But then again, Mars has clouds, and so if these exoplanets are similar to that, then even a very thin atmosphere could make it difficult to see. Yeah. Oh, yeah. Okay, so one is if you found that an inner planet had lost its atmosphere, what is the next best step for motivating a search for biosignatures on a habitable zone planet? To keep observing cost low, should you just keep hopping to the next innermost planet to determine if it has an atmosphere? Yeah, so that's a great question. So I guess kind of thinking about this in terms of the TRAPPIST system. Again, this method starts to break down once you get to habitable zone temperatures. And also, overall, it's very difficult to observe secondary eclipses when you get to habitable zone temperatures because they're just cold enough that the planet is not emitting a lot. So if we were to observe like TRAPPIST-1b and TRAPPIST-1c, the two interior to the habitable zone planets, and found that neither of those had an atmosphere, then honestly, I think the best thing you could do at that point is to just do transits. I'm hoping that that wouldn't be the case because that's definitely the one where it's like, well, if they don't have an atmosphere, you don't want to just assume the other planets don't have an atmosphere without looking. But in that case, yeah, you wouldn't really be sure whether they would have an atmosphere. It would be much more difficult to say. And then there's another question. How concerned are you with stellar activity disrupting this neat, efficient atmosphere detection approach? Yeah, okay, so that's a good question. So the other nice thing about observing in secondary eclipse is that we don't generally have to worry as much about stellar activity as you do when you're observing in transit. And that's because a couple of reasons. So one is like, for example, when you're observing a transit, if your planet transits a star spot, then that can cause like, that's a big change in like the type of the temperature of area that it's going in front of. And so that changes your transit depth and everything that you're seeing. In secondary eclipse, you don't have to worry about that because you're not looking at the planet actually like going in front of part of the star. So you don't have to worry about, is it going in front of a part of the star that's as spotted as the rest of the star or anything like that. You're just like, the star is constant and then your planet's going behind it. And so the only thing you have to worry about is if you're stacking multiple eclipses, is your like star rotating during that time scale, and then like if one hemisphere of your star was like significantly brighter than the other hemisphere, then that could be a problem. But it's generally less of a problem than it is for transits. Yeah.
I had a quick surface question. So how well do we know if you had a granitic surface, say, and you expose it to billions of years of a high radiation environment around one of these low mass stars, do we know how that might change the reflectance spectrum?
Yeah, that's a good question. Do I need to repeat that one, or were you standing close enough?
I was close enough.
I have no idea. That's actually a really interesting question. I mean, I guess like are studies of like space weathering of asteroids, but I have no idea if that would operate the same on like a large planetary body. So yeah, that would be an interesting question to look into.
Last questions here or online? All right, well, if not, that's all. Thank Megan again. And for the people in the room,